project, and this is actually in its 7th stable release this summer. We are a couple of Harvey Mudd students, Amelia, Carli, myself, David is from Villanova, I'm from Stony Brook, Errick's also from HMC, Mikayla is from Rochester, and Zach is from Vassar. And we are working on things including chord voicings, theme weaver, which takes a bunch of melodies and adds them to your solos, guide tone lines, which help soloists, and real-time audio input, so that you can actually record your solo. First up will be the chord voicings, as chords are the foundation of jazz. With Errick.
How's it going, folks? Alright, so we're working on chord voicings, and so to explain this adequately, we should start with what a chord is. Ooh, I have buttons. Alright. A chord is a stack of notes that are played simultaneously to produce a sound. That sound can evoke any type of emotion depending on what kind of person you are. So it can be happy, sad, or a little bit confusing, you know, whatever you want. A voicing is the order of that stacking. So, for instance, if you wanted to play a C chord in root position, you play C, E, G, that's the root position, that's one voicing. However, you can move different notes up or down an octave. So for instance, I can move the G down an octave, play a second inversion C major. So now you have G, C, E. You can also spread chords out. And so you can have, for instance, a C, G, E. I can stretch that far. So that's a whole different voicing, moves the E down or up an octave. And then you can also add notes that did not appear in the chord originally. So this is a C6-9. And so what you'd have is a C in the bass, which is not pictured here, a D, G, A, and an E, sorry. And so the A is the 6th that was added. And then choosing voicings, there's certain rules that that need to be followed. So usually you want a voice lead, which means you want to bring notes naturally to the next step when you bring in a new chord. But those are generally guidelines, so like every rule is kind of meant to be broken. So in this sense, you kind of follow that as a guide, but eventually you kind of add your own artistic flair. You can do whatever you want. The first way to make a voicing is to basically choose the best one that falls within the set of constraints that you set. So for this, we have 2 boundaries, one at E and one at a higher octave E. And so you want to see which chord falls between those 2 boundaries, and the first and second inversion are falling there, so you would choose one of those 2. The second way is that you can just build a voicing, and that's that. It's pretty simple. So the way the program currently works is we have a high note, a low note, and then different voicing types that you can choose from. So these parameters here, except for this custom button, which is what we've added, these are all the parameters that it would choose voicings on. It would have a high boundary, a low boundary, and then it would choose the octave and choose the voicing based off of that. You also have open, close, choral, shout, and there's different other voicing types that aren't listed as well. But that's how the program would choose that. And so it starts with the voicing type, and then it narrows down the chord using voice leading and also using the general range. And then it takes that chord that it chooses and repeats it. There's a comping pattern. And so rhythmically, you might want to play a chord like, and so it'll repeat that one voicing that it chooses. Yeah, don't make fun of me, that was nice. It'll choose that, all right. I'll reopen and then close it. And then close it. All right. So that's the current pattern, and what we've instituted, Dan will explain with our new algorithm.
Okay, so the current Improviser algorithm, as Errick has explained, kind of looks at an existing database of voicings and searches for one that fits and plays it. But we thought it'd be really cool to break a couple of rules and generate our new voicing. So the way we do this is we start with all the valid notes. So for example, a C chord, simple C chord, C, E, and G, right? We just apply a weighting to all the C's, E's, and G's within the piano's range. And then we'd apply constraints. So for example, we don't want any notes lower than a certain note or higher than another note to get fewer options and choose easier. Now, we randomly select a certain number of notes within that range, but we weight the notes so that your more desirable notes are more likely to get chosen. So in jazz, like the 3rd and the 7th, so in a C7 chord, an E and a B flat would be more likely to be chosen than a C and a G. But all of them could be chosen potentially. Now, we have many more parameters than the previous algorithm, so you can custom tailor your voicings. Our parameters are, some of them, well, we're trying to mimic a human's hand while playing the piano. So we've got left and right hand parameters such as stretch limits. So for example, some people can stretch a 5th. I personally can stretch about an octave and a 4th. So you can sort of tailor that to how much you want the hands to stretch. Absolute limits say maybe you don't want to go above this E here or below this C here because otherwise it sounds muddy or too high. You can have a minimum and a maximum number of notes, maybe 3 notes in one hand, 2 in the other. And color priority. Color notes are notes that aren't actually in the chord but can be added to give the chords a different kind of feel. We also have single selection parameters, 3 of them for voice leading, so that will sort of control how much the piano is allowed to jump around. 2 motion parameters controlling how much the hands are allowed to jump around. We have probability for repeated notes, so for example, if I play a C down here and I'm only playing 3 notes, I might not want to play a second C. I might want to make it more likely that I'm hitting a G and an E as well, right? And we have 2 cluster reduction parameters because sometimes playing a bunch of notes close together in a dense jazz chord like this sounds really bad. So our advantages are the fact that we can custom tailor our voicings much better because we have more parameters for the user to choose from. You can tweak voicings without changing the overall sound, which is sometimes really helpful. We have more voicing options and novel voicings, more variation in the same lead sheet as well, because for example, as Errick said, you might be playing, the old system might be playing a clave pattern like this. Whereas we might go and change the voicing so it sounds more interesting. And we can save our settings, so if you really like your settings once, you can save them and use them again. So we're going to show you a quick demo here. The tune is called St. Thomas by Sonny Rollins. We're using it because it's got really quick chord changes and it's got a short melody. We're going to play the melody as played by Sonny Rollins. Pay attention to the piano, because that's sort of what we're mimicking. I'm going to play the standard system that was already implemented, as well as 3 custom voicings we generated with the program. And just to let you know, the rhythms are generated by the same random rhythm generator. So that we didn't really change much about that. So listen to the notes, not the rhythms. Here's the song, and 36 seconds. Okay, so that's the melody, and here's how Improviser currently voices the chords in that melody. Oh wait, no, that's not good. That's what we want. Okay, so as you can tell, they're kind of very similar in the way they're voiced, same kind of range. We can do a lower voicing than Improviser, for example. Sorry, stuff's happening. It's very strange.
You're not in presentation mode anymore.
Yeah, well, this is rather convenient. Oh wait, I'm pressing escape. Let's do it. Let's reload the page. That would do it. There we go.
You go back to presentation mode.
Yeah, just like get to there. Okay, so before that happened, we were showing a low voicing. So here we go. it was very similar to the original improviser voicing, low and kind of dense. We can do a sparse or higher voicing too. So that was only 3 notes per chord as opposed to 5. And here's the last one we have. This is the left hand's going to be playing the chord, and the right hand's going to be playing basically a solo by just picking 1 note at a time. Oh, well, YouTube's doing well today. Now we have Amelia, who's going to tell us about themes.
Hey guys, what's up? I'm Amelia. So this summer I've been working on the Theme Weaver in Improviser. This is a project that was started at the end of last summer, so I've been further developing it. So first we should talk a little bit about what I mean by a theme in this context. So a theme is like a short melody that is played repeated throughout a solo. So here we just have a short 4-bar solo and have arrows pointing to where the themes are. So the process of generating a solo in the Theme Weaver goes like this. So first, the user chooses a bunch of themes, and then the Theme Weaver decides whether they're actually going to use a theme or not. So if yes, then you choose a theme from the list, apply certain transformations to the theme to make it a little bit different so it's not the same thing over and over again. I'll talk a little bit about those transformations later. And then you add it to the solo. If you were to not use the theme, then you would generate a melody that's unique to the theme and then add it to the solo. So these are the transformations that we can apply to the theme to make it a little bit more interesting. These are all standard jazz transformations. So up at the top, we have the original melody, the original theme. The first transformation is transposing the theme. So this is moving the melody up or down 1, 2, or 3 half steps. This keeps the same shape and contour of the original melody, but changes the notes a little bit, so it's not exactly the same. Then we have inverting the melody, which basically takes the melody and flips it over a sort of horizontal axis. So whatever was originally ascending would be descending, and vice versa. So the opposite of this is reversing the melody. So instead of flipping it about a horizontal axis, it'd be flipping it about a vertical axis. So you can see how it's changed there. The next one is expanding the melody. So this we can either expand by 2 or 3 times the original duration. So what this does is makes each note either 2 or 3 times longer than it originally was. This keeps the same melody, but adds a little bit of a different character and different vibe to it. It's changing it up a little bit. Next one is side slipping. So the way this works is you take the original melody, you play that, and then you play the same thing except transposed up or down. And then the last one we have is bar line shifting, which is similar to side slipping, except instead of moving vertically, it moves horizontally. So it moves forward or backwards a beat or so. So we're going to do a little bit of a demo of how the Theme Weaver works. I'm going to find where Errick closed it.
I did nothing wrong.
You did close it. So this is the Theme Weaver. So first you can go ahead and choose which theme you want. So I'm just going to do one. You can choose multiple, but we'll just do one. I'm going to set all the probabilities to 0 to 0.2. This is the probability that a certain transformation will be done to the theme before it's added to the solo. You can change the order the transformations are done in. If you can imagine that if they're done in a different order, then the final outcome will be a little bit different. This up here we have the probability of actually using a theme or using a different way of generating a solo. And we can go ahead and play the theme here. So that's the original theme. next we have Carli and Mikayla talking about the guide tone lines.
All right. So this summer we've been working on the automatic generation of what are called guide tone lines. So first of all, what is a guide tone line? So a guide tone line is a smooth line, meaning melody line, of tones, meaning notes that are supposed to guide you through the chord progression. So what does it mean for something to guide you through a chord progression? So all the notes here belong to the chords that they are played over. And a good guide tone line, if you hear a good guide tone line being played, your ear should be able to infer the chord changes that are happening from just a single melody line. And this is what's known as playing the changes. Guide tone lines are really useful for people who are just starting to learn how to improvise. A lot of people will start, when they're learning how to improvise over a certain piece, they'll just play a really simple line, like, okay, how can I get through this piece? And then later, they'll be like, okay, now let me embellish this a little bit and make it into an actual solo. But then, like, first concern is, okay, I want to get through this piece in one piece. Alrighty, so generating guide tone lines. So we've got a bunch of different parameters you can set to kind of customize your line. You can pick what note you want to start the line on, and that acts as kind of a seed for the generation of the rest of the line. And actually a fresh line gets generated at the beginning of each section of the song. Because like, I guess a section marks like a big change in the song, like the style could change, or like the style is kind of like the rhythmic pattern going on in the background, marks the beginning of a new part. So you can select the range. So if you play like flute, for example, you probably want your guide tone line that you're going to follow to be a little higher than if you play the bass guitar. So having a range is good. If you start to get too close to the boundary of a range, the line will just turn around, go back the other way. You can have two different types of lines. So what's called a single guide tone line is like one smooth line, and then a compound line, you are really jumping between two lines, like a high line and a low line. And if those lines start to converge, the program will make them diverge again. And then you've got like a max duration of the notes in your guide tone line. So let's say you're just a beginner and you really can't keep up with the changes very well. Maybe you want your guide tone line to just be whole notes to start off with. The whole notes are longer than like quarter notes, which would be moving a little faster. Your direction of your line, so your line can be like generally ascending or descending, and then how much color you want in your line. So you can choose to allow what are called color notes, which are notes that aren't strictly in the chord, but are kind of like extensions you can add to the chord to make it sound more gritty. Okay, so we start with our seed note, and we have like a successor function that chooses the next note. So how do we choose the next note? So we choose from all the chord tones, or if you're allowing color, all the chord tones and color tones that are closest to that note and are in range. And then we use a scoring function that takes into account the distance from the previous note. So we want these lines to be smooth. We don't want them to be jumping around all over the place. So we want a small distance from the previous note. The direction that it's going from the previous note, like if they want an ascending line, we don't want descending notes to be valued higher than ascending notes. And then the priority of the note in the chord. So certain notes are more important to the feel of the chord than others. The 3 and the 7 are like generally like they give the chord its character more than like the 5, which is sometimes even just left out when people are playing the chord. So, yep. I've got some demos of what these lines sound like. So this is a single guide tone line. Okay, and this is a solo generated over this line. So this solo was generated using a set of transformations that were learned from about 9 Charlie Parker solos, and Carli's going to explain that in the second part of this part. So the cool thing about that is you can still hear the underlying line underneath this. So this gives someone the option to basically like paint their solo. Like, I want it to go down and up or whatever. I want it to follow this line, and then we make it cool, I guess. And then here's one with a compound line. So you can see it's going to jump back and forth between the low line and the high line every 2 notes. So the first note's part of the low line, and the second 2 are part of the high line, and it goes every 2 notes like that. And why we do that is we want there to be more motion, like, inside the measure, and then less motion when you're going from, like, one chord to another chord, because that gives, like, a stronger pull when you have, like, half step or whole step motion in between measures like that. Let's see. And then here's a solo generated over that.
Alright, so transformations. So what a transformation does is take a very basic outline, so like a guide tone line, and it adds embellishments and includes motifs to make it more complex, so more like a solo that someone would play. And so we have a grammar that defines these transformations that gives certain conditions under what notes they can be applied to, and from that we're able to generate solos through these grammars. And so what we've been working on this summer is sort of improving the transformation learning so that you can learn transformations from a solo and then apply them to guide tone lines, and hopefully they sound more like what a human would play. And so we do this by taking a solo that someone's played and flattening it to an outline, so flattening it to a guide tone line, and then we divide this up into windows, and then for each window we learn a transformation of how you went from the solo to the guide tone. And so here's an example of how you can sort of hear how it flattens.
It's a very small box.
Well, you can see the solo, and here is the flattened melody from it. And so that sort of maintains the shape of the melody that was there before, and it gives us a way to figure out what transformations the artist used to get from a sort of flat line to a solo. And so we do this with the windows. So the old way it used to do it was take each note in the outline and figure out what was subtracted from the original melody to get to that, and that becomes a transformation. And so what we've been working on is sort of playing around with increasing the window size or changing the conditions under which these transformations can be applied so that you can sort of maintain the shape of the solo that was there before, and then when it's applied to a guide tone line, it will maintain the shape of that line as well. So if you see before, it would take one note, and you kind of lose some of the information of where that transformation is leading in the solo. But if we increase the window size to 2 notes, we can see in the solo that line kept going up, whereas if you had split that up into 2 different transformations, you wouldn't have really gained that same information. And so that's how we've been working with generating solos using guide tone lines. And here's David and Zach on audio input.
I'm David, this is Zach. We've been working on a different part of the project, dealing with real-time audio input. Now, one thing that's interesting about real-time is that we're not doing any of the stuff post-processing. We're not using any algorithms that take a look at files that have already been created. We're looking at an incoming stream of information. And the thing that's different about this incoming stream of information is that it's an actual audio signal. And formerly, what Improviser was using was something called a MIDI interface. This is a universal interface for electronic instruments to send signals like note on, note off, and how hard the key is being pressed with electronic instruments such as this piano. And you can already see the cable that goes in and their drivers. It's a very standardized system.
Okay, so for this we used a real-time audio processing language called Super Collider. And Super Collider is very effective at what it does for several reasons. Because it has a client-server architecture, so that means that there's two separate components of the language, kind of like the way that a web browser works. Very interesting. So the server is known as SE Synth, and it acts as a highly versatile real-time scheduler. So you don't have to worry about whether things are going to happen on time. When you program, you just send something up to the server, and it handles all the scheduling for you. And the language, like I just said, it actually just sends stuff up. It actually plays functions. So if you send it a sine wave, a sine function, it will play it. So here you can see a bit of our code that we use. This was the part that was actually tracking the frequency of the incoming information. And down here you can see it's actually playing that function. Okay.
So now that we have a structure to process the signals, let's see what the actual signal looks like. So right here on the left, this is what's called a spectrograph. And on the y-axis, you have the frequencies, and on the x-axis, you have time. But this is actually a three-dimensional graph. The intensity, or the amplitude of a sound or a frequency is mapped with the color. And if you could think of this as a mountain, this is a cross-section. Now this graph, I've turned it sideways and flipped it just to map it onto it. But it shows a whistle being blown at a frequency between 1 and 1.5 kilohertz. And it is measuring the amplitude right there. And as you can see, there's a lot of background noise. This is a real audio signal. And so the major goal is, how do I isolate the fundamental frequency from an audio signal in real time? Now, a whistle is very clear, but other sounds, such as a voice, have what are called overtones. And if you see this, if you see this really loud bar, there's actually oftentimes with something like a voice, there's little shadow bars that are other frequencies that make up that note. Most notes that you hear actually are made up of smaller notes that combine to form this sound that your ear interprets as a single sound. And how we do it is the fast Fourier transform. Now, I'm not going to go ahead and explain the Fourier transform, but what I really want to highlight is this fast part. So Super Collider does this really neat thing where it can actually perform this calculation. It's an n log n operation about as fast as the sampling rate. So it could do it hypothetically at 44,100 times per second. And now that would require a lot of CPU power, and what we actually end up doing is doing it about a 64th of that. So we end up with about doing it 690 times per second, which is, first of all, incredible. I really want to relay that to you, but it just allows us to get enough samples and enough clips of sound and frequency into a buffer, which Zach will explain.
Yeah, so when we got the FFT, it will translate, time domain into frequency domain, so you get a bunch of partials. But once we have that, you have to get the fundamental. And so, as David eloquently put, there's a bunch of overtones that obscure the fundamental. So a lot of time, a very common problem you get with pitch detection is a bunch of very quick octave jumps, because the most prominent fundamentals are an octave apart. And so the way that you get rid of very quick outlying values is take a median. So you just run a buffer a buffer and just take a median, and so that will ignore a lot of the outliers while still maintaining a lot of accuracy in your measurement. So So, and another problem is that the FFT is actually spitting out values even when it's silent. So you get white noise, which has theoretically infinite frequencies, so you get a bunch of jumping around messiness. So the way that we fix that is by only considering frequencies when a note onset has been detected, which brings me to how we detected onsets. Two ways to detect onsets are with an attack, and which means that we were literally just looking at how loud the noise is. So if you hear an audible spike in volume, start your measurement, that counts as a valid frequency. And then also to detect when a note is changed. So that the way you would do that is you have a larger window along with your one frequency tracking, but a larger window that's saying, okay, am I playing a note? Okay, has the frequency changed over this much larger window? And that's how you detect a note change. So we have a little demo of our program working with Improviser. Yeah, so there you can see Improviser on the left and our module on the right, doing all of the conversion from audio to MIDI.
You have to click in the.
I have to click in the gray.
After you play video.
Okay. So now that we've gotten that to a working state, we've kind of split off into more stuff with interactive capabilities of Improviser. So in jazz, it's very common to want to trade with another jazz musician or soloist. So a common practice is trading fours. So one soloist plays 4 bars, and then the other one plays a response of 4 bars, and it goes back and forth arbitrarily long. And we would like Improviser to be able to do this. So currently, Improviser is able to do this to some extent by deterministically, before you start trading with it, it generates all the solos it's going to play. So it just generates, and it will not react to you as a user at all. And we want to change that so that it actually responds to what you're playing the way a human soloist might. So kind of play things similar or, in contrast to what you just did. And what makes this challenging is the fact that since you have to perform calculations to the sound that the user just put in, to the MIDI or the notated notes. And that's hard because we're dealing with Java, which it's hard to schedule things that accurately. So the way that we're fixing that is by building a very primitive scheduler to get this running so that before you have to play something, you just before that you do the processing and get it to the MIDI client just in time so it can be played in time. Now David's going to talk.
Where I've branched off and started working is drum beat and style detection. So the process that I'm working with is currently we're dealing with something called monophonic sound. So as Dan's sample of playing trumpet or a flute or a recorder, it's a single tone. You can do this on a piano, but you can't isolate chords for a lot of reasons. And basically this is what a monophonic tone sounds like. This is a clave sample that's being played, and you can already even tell the clave has a frequency, so it actually plays a sort of note, and you can see that it's made up of those overtones, a ton of little tones, and then a fundamental frequency. I couldn't tell you which one it was, but you can see that there are these bars. And what I'd like to move towards working with is polyphonic sound. Now, a drum kit track, this is a simple breakbeat sample, looks a lot like this. And there's 2 ways of approaching this problem. Now, hopefully, I'd like to isolate bars and perform our calculations in parallel over these stripes. So maybe from 0 to 1 would be a bass drum. And from 4 to 5K, it might actually be the ride cymbal. Unfortunately, this isn't as simple as just isolating boxes, and there are actually fundamental frequencies within percussive sounds. as well. And so once these sounds have been extracted and placed into a MIDI file, the improviser can actually take those MIDI files and create a style profile, which looks like this. So this is how you would enter it into a system. And then here, if you can read these, it actually says ride cymbal, closed hi-hat, acoustic snare, and there are these probabilities associated. So what the style will do is try to mimic the way a drum player would switch off between these different types of playing drums. And that is it.
By the way, you will be getting in your email very shortly a survey regarding chord voices, if you'd be so kind. I would really appreciate some feedback on how they sound. And also to answer a question these guys asked me when they took it, they're not always in the same order. You might be getting the standard first and the custom second, or the custom first and the standard second. So base it on what you hear, not what you think.
Okay, time for a question. I know we ran over, but maybe something you'd like answered.
Was the theme mover already part of the improviser?